Okay, let's start this again. All right, so I want to do this integration here. It doesn't look like anything we've ever seen in our.
Professor,
Yeah.
We still
the
can't see the
top of the
top.
board is still a little cut off.
Oh, hold on a minute. Sorry about that. Is that better?
Thank you.
Thank you.
Okay. All right, sorry about that. So I've got this hideous evil problem here. So the only thing that makes sense is to pick the u from something with the roots. So what I did was I went after the smaller root and I said, if I call that one my u, then technically wouldn't that be u squared? If I thought about it from that standpoint. Now the problem is I'm not going to have a du sitting around, but this is the impetus. If I let u be the fourth root of x, then that means x is u to the fourth. Oh, and then what's dx? I don't have a du, I find dx. Dx would be 4u to the third du. So this form of substitution says I'm going to replace x with a function of something else, exactly the same way we do with the trig sub. So now let me go back to the original part here. If this is a true statement, then this is u, then this is u squared. And then this is 4u cubed du. And look what happens to my integration now. My denominator is 1 plus u, which is a lot friendlier. My numerator is u squared times 4u cubed du. Now that might look a little intense, but it's a rational function. And as an absolute mathematical statement, every rational function that exists, if you made up a polynomial and you divided it by another polynomial, that can be integrated, period. It doesn't mean it's always going to be easy, but it absolutely always can be integrated, and only using techniques we've already learned in this course. Whoa. So I have a really simple denominator. Now that numerator is not quite friendly yet. Let me finish off the numerator. So how about I write the numerator as 4u to the fifth over 1 plus u. Now, any suggestions?
Long divide.
Or what's a little bit faster?
Partial diffraction.
No, not part. I only have one denominator, but long division, or what's its sister method, if you will.
Synthetic.
Synthetic would probably be a little bit faster. If you're not well versed in synthetic, then go ahead and do long division. Synthetic's just a little bit faster and probably less errors. So this is u plus 1, so the root is -1. Remember, the root is whatever makes the denominator 0. So I put the -1, and if you remember, I put the coefficients in descending order all the way to the constant term. So it's 4u to the fifth, 0u to the fourth, 0u to the third, 0u squared, 0u plus 0. I must have that many zeros. If I was doing this as a long division, I would write 0u to the fourth, 0u to the third, and so on. So if you guys remember, you bring down the 4, and then you mama the problem. I learned that from a student years ago. Mama is multiply, add, multiply, add, multiply, add. Just keep going. So -1 times 4 is -4, add them. -1 times -4 is 4, add them. -1, and so on. It's good to remember how to do these because they come up often enough that it's useful. Now remember, that's my remainder term. So that's the constant, the linear, the square, the cube, the fourth power. And that makes sense. I have a fifth power over a first power. My answer should be a fourth degree polynomial. So what I'm going to get is 4u to the fourth minus 4u to the third plus 4u to the second minus 4u to the first plus 4 minus 4 over u plus 1. And there's a du in there somewhere. Now, that is easy to integrate. Okay. Now, depending on the degree difference determines how many terms, but there's nothing about that process that should be terribly taxing. So now let's integrate that bad boy. So I'm going to get 4/5 u to the fifth minus u to the fourth plus 4/3 u to the third minus 2u to the second plus 4 times u minus 4 times the natural log, and I do need the absolute value. Now we're done with the calculus. Now, the question is, how do we represent our answer? What would be the cleanest way? Should I try to write roots all over the place? Or might it be easier if I leave things as fractional exponents? What do you think? Roots or fractional exponents? By the way, it doesn't matter, but you got to pick one and stick with it.
Rational exponents.
I'd probably go with that. I don't like writing something to a power inside a root and all the parentheses. Sometimes it just gets hard to read. So if u is the fourth root, that means u is x to the 1/4, then this would be 4/5 times x to the 5/4. Then this would just be minus x. Oh, okay, that's nice. Plus 4/3 x to the 3/4 minus 2x to the 2/4, or just x to the 1/2, if you will, plus 4 times x to the 1/4 minus 4 times the natural log of x to the 1/4 plus 1. X to the 1/4 is non-negative. Fourth root of a number can't be negative, plus 1. So if you choose, you can do that. Now, that's my answer. I really don't want to take the derivative of that to compare it, but that's how we get. Now, what made this problem difficult, first of all, is there's no chain rule factor. There's no way I can do a simple u sub like we did in count one because of the chain rule factor, but through the appropriate choice of an exponent. Now, if I had chosen my u to be the square root, then we would have had a problem because this still would have been a root. So I chose the u to be the smaller of the two. So let me ask you a simple question. Okay, similar question now, similar problem. Let's suppose the question involved, how about square root and cube root? Let's say that was the question instead, because it's the same overall kind of problem. What do you think we should pick our u as? Remember, what made this work was I could write this as u to an integer power, and I could write this as u to an integer power. I want to get rid of fractional exponents. So what would be a really good choice for my u?
U cubed.
X cube.
That
X to the x 6 root.
sixth root. It says pick u to be x to the 1/6, which by the way would mean x is u to the 6th, because that's 1/2, that's 1/3. This is smaller than both, which would now make this a u cubed, and it would make this a u squared. So that's a perfect answer. Excellent answer. Does everyone see that? If I make my u the cube root, then this is still a fractional exponent. If I make my u the square root, then this is still a fractional exponent. But if I pick my u to be something smaller, my exponents were 1/2 and 1/3, 1/6, think like common denominator kind of thing. 1/6 cover me. So this problem here is a little bit trickier. So that's what we do in this case here. So that's actually a perfect answer. Okay, hold for just one moment. I have an important call coming in. Let me pause this.
The bottom line, it would still work out.
When you say do it, are you talking about this problem here?
Yes, can't you still do it the same way as the other problem?
Well, what made
I understand this is way easier, but like just in case on an exam you don't see that.
That is the question of the day. We couldn't do this period. What made this problem work is that I made it into a rational function. Okay, that's the key. I made it into a rational function, and I just said you can always integrate a rational function. If the degree of the numerator isn't smaller, then you do the longer synthetic division. But if I still have a fractional exponent, there's no longer synthetic division to perform. In other words, if I had picked square root or cube root, one of them would still be a fractional exponent, which means it's not a rational function. So I'd kind of be dead in the water in that I can write it, it would be correct, but I really wouldn't be able to go any further.
Understood.
So that's why. Now, what if you just weren't very lazy and you said, oh, I'm going to pick to the 1/12th power or the 1/18th power? Actually, any multiple of 6 would have worked. You want the smallest one, because do you realize what would happen if you did 1/12th power? This would be really long and you'd have a lot of combining and canceling. Yeah, so this is the best choice based on this type of problem. Now, this is one type of problem. This is one where I took something that was evil and hideous and I changed it into something that we could do by making them rational functions. So we're going to continue kind of with that theme because rational functions are what we have been practicing. I mean, that's the partial fractions decomposition, for example. That's what made the trig subs work, is we made them into things that we could do. We really don't like the roots. That's really what it comes down to. Roots in the integrals make things harder for us. So let's try another one. I don't want to say it equally evil, just a different form of evil. All right, I have the integral of e to the x plus e to the negative x over e to the x. Oops, sorry. Try that again. Over e to the x minus e to the negative x dx. I think it's safe to say that this one just looks terrible. Well, why don't we start with something like let u equal e to the x. If u equals e to the x, then what is e to the negative x?
U to the negative 1.
U to the negative 1, or therefore 1 over u. That'd probably be easier to think of it. You're right, it would be u to the negative 1. Now, there is no chain rule factor in this problem. So that's not the way we're going to go. We're going to then say x would be the log of u. Then my dx will be 1 over u du. We're going to take this route. And by the way, there are more than one correct routes to take for this problem. That's not the point. I want to take a route that mimics what we're doing today, and that is replacing x with a function of something else and just seeing what that provides. Here's my ironclad money-back guarantee. When I do this, this will become a rational function in the integral, and I can integrate that. No matter how ugly it is, I will be able to integrate that. So let's start subbing. That will be u plus 1 over u, u minus 1 over u, and then times 1 over u du. So let's clean this up if we can. So why don't I first, let me go ahead and multiply this in the denominator. Then my denominator will be u squared minus 1. Okay. Now I have one more step. I don't like the fact that I have a quotient in my numerator. So what I'm going to do is multiply numerator and denominator at this point by u. In other words, go like this, u over u. And now my numerator will be u squared plus 1. My denominator will be u times, how about if I write that as u plus 1, u minus 1? Because u squared minus 1 clearly factors. So everybody okay with that? And quick check of your algebra, just so make sure you agree that your algebra is sound, that this quantity here is equal to this quantity here. Boy, that looks scary, or does that look like something we know exactly?
Partial fraction.
Partial fractions. In fact, this is the least dangerous because I have 3 linear factors. None of the numbers are particularly big. So I'm quite happy to do this using partial fractions. Right now, my denominator is 3rd degree. My numerator is 2nd degree. So I do not need to perform any algebra before I start. My numerator is already smaller. That's key. Let me throw a what if at you. This would be the worst possible problem. What if that were a u to the 4th? What if? Because I could have changed it. What if my numerator were u to the 4th?
Then we do division, long division.
Yeah, but before we did long division, that would mean we'd first have to multiply that completely out, get our cubic, then do long division, then refactor it. So we'd actually have to go backwards almost. It isn't. We're not worried about that.
Can't you build a perfect square?
Well, the problem is it's a u cubed though. Right? It's a 3rd degree polynomial, so that won't help. Yeah, unfortunately, If my numerator were too big, I would have to have a polynomial on the bottom, not a factored polynomial. So if you remember the problem that we started with yesterday, I started with one where the denominator, I think, was a quadratic and our numerator was a higher degree. We did the long division, then we factored the denominator. That's probably the longest problem you can face. This isn't not that thing, so this is much, much easier. So let's set this up. So u squared plus 1 over u plus 1, u minus 1 is a over u plus b over u plus 1 plus c over u minus 1. So when I multiply through, again, unless we make an arithmetic error, this should not be a difficult manipulation.
Professor, just to double check, if we have if in the denominator, if there was a multiple of square, I mean, if it was to a power of 5 or 6, right? We don't do partial.
If I say in this one, if I had a large exponent,
Yeah, if we had a large exponent, you showed us another way.
yeah, but unfortunately, we have too many factors really to apply that way. So if I have a large exponent, that's when I change my major and I run for the. No, I'm just teaching. If that problem even did come up, we would need alternate methods. That would be. Remember, I said there's more than one way we could attack this one. I'm going to actually show you alternate versions of the attack because, quite frankly, if an integral is presented to you and you don't see one route, but you see another, and I give you an example to start the class. I give you an integral where the denominator is a difference of squares. And one person sees clearly a trig substitution, another person clearly sees a partial fractions decomposition. Well, can they both get the right answers? Yes, because they're both valid ways of doing that particular problem. If there's more than one approach, okay, take it. When the first day I introduced integration by parts, I purposely made a poor choice on my U and dv, and then we did a different choice. Because I made a poor choice and it ended up getting worse, we didn't stop and say, okay, well, let's just give up on this one. I said, no, we'll try something else. So that's really what it would come down to. If you found yourself in a position where you now said, I got this problem way harder than the one I started with, then we probably need an alternate route. I'm assuming there's no error occurred. Now, this is about as friendly as we could hope for in this context, because look what we started with. And look where we are now. This I can deal with because this is not bad. So let's start by picking, how about
U squared plus 1. U squared plus 1, not minus.
0.
thank you. Oh boy, that would have mattered. Yep. Thank you.
U
So
equals
let's start,
1.
let me start with u equals 0. The left side will be 1. The right side will be 0, 0. 1 times -1 is -1 times a. That would imply that a is -1. Let's pick u equal, how about +1? Then my left side is 2. If u is +1, 0, 0, 1 times 2. Agreed? So that'd be 2c. Wow. I'm kind of happy with what's happening so far. We don't even have fractions. Most of the time, I would just expect fractions. And what should my third choice be?
-1.
Negative 1. And the left side, I have again 2. So 0, 0, -2 times -1, that'd be 2 times b. So if I did this correct, yeah, that looks beautiful. All right. So that means this part here was -1 over u plus 1 over u plus 1 plus 1 over u minus 1. So my integration would be the integrals of -1 over u plus 1 over u plus 1 plus 1 over u minus 1 du. Well, obviously, I'm going to have a whole bunch of logarithms. Is having a whole bunch of logarithms probably a good thing? Yeah, because the relationship between u and x in the first place involved exponentials and logs. So if I have a bunch of logarithms, translating back might be a fairly simple thing. So this will give us negative log 1 over u. Oh, I'm sorry, what am I saying? Sorry, negative log u. Getting ahead of myself there. plus log absolute value of u plus 1 plus log absolute value of u minus 1. Now, question. Can I manipulate this? Should I manipulate this? I mentioned logs before. You can always manipulate and you never have to. I said there is a time when you really do want to manipulate them. Would this be that time? In other words, using log properties to combine them.
You did mention that you'd like to, if you have a variable, you just want a log of that variable by itself.
Well, here's the thing is, if I have coefficients on all of these, then the coefficients show up as exponents, and then I've got things to various powers. And we talked about that. Is that better? Is that worse? And I said, generally, when your coefficients are the same, it means you're not going to have any exponents, then combining the logs might make more sense. But remember, I have to convert back at some point. So it might be prudent to have only one logarithm. I can, by the way, I can certainly sub back at each stage. But then that answer, I'm going to have logs of e's, which just for some reason that just doesn't feel right yet. Can we write this as one logarithm? The sum of the logs is the log of the product. The difference is the log of the quotient. So this would be log of what? Of u plus 1, u minus 1 over u. Everybody got that? That's what this would be. That guy would end up in the denominator. Wow, is that better or worse? Well, actually, I can make this way better. Multiply out your top. And now what have you got? U squared minus 1 over u. Now, my favorite algebraic process. If I do that, now what have I got? There's a plus c in here. Okay, I don't want to lose that plus c. Okay, now what have I got? Log of u squared over u minus 1 over u. Now, why would I want to do such a crazy thing? Oh, it's right there, isn't it? You see it? This is why, in this case, this was probably a really good idea. Because this quantity here is equal to this, which is equal to this, which is equal to this. Now, if I walked away, if I never subbed back, this is a shorter, it's a cleaner answer than this. These are equal.
If we finished with that whole shebang, is that going to be then partial credit?
Well, but we're not finished with the answer yet, though. We still have to sub back.
Right. I mean, like if we converted with the negative natural log of u plus natural log of u plus 1 and natural log of u minus 1 plus c, and we converted there, that would be partial credit.
Oh yeah, yeah. You haven't said anything wrong. You haven't said anything.
No, we just didn't complete the.
But the fact is, can I go a little bit further? Let's go one more step. If I substitute back in, what's my answer? Log of
natural log of e to the x minus e to the negative x.
Or by the way, e to the negative x or 1 over, I don't care. In fact, let's write it as e to the negative x because that's the way the problem was originally written. I think we would agree that may be the easiest answer because it's the shortest. It's a few, I don't have any exponents. So this is the final answer to the question. Is everybody cool with that? Oh, okay. Wow. What a monumental piece this was. This was huge. But everything we said was true and correct. It's the path we chose that I wanted to emphasize, not the answer. There's other ways we could have got this answer. Believe it or not, there were other routes we could have taken to get this answer. In fact, I hate to tell you this, but we could have got the answer in one step. Some of you may have noticed. Now, I didn't want it. I wanted to do this on purpose to illustrate the method. What do you notice about the numerator and the denominator of this? Well, obviously they're different, duh.
They look like reciprocals.
Not reciprocals.
Well,
look at the denominator. Now look at the numerator. Do you notice anything? What's the derivative of e to the x? E to the x. What's the derivative of?
Oh my God.
X?
I was gonna say that in the beginning.
God.
Is my numerator the derivative of my denominator?
Yeah.
Is it? Yes. So therefore my answer is log of the denominator. Now, that wasn't the point. The point was to illustrate the being able to do this technique. Because what if the numerator wasn't the derivative of the denominator? You know, what if I had one small detail, you know, What if there was one small thing that was different? The process. I wanted to illustrate this process. Now, if I ask this question in Calc 1, I would say, well, that's my u, that's my du, my answer is log of this. Oh, I'm done. Yes. That's kind of a quick check. Now, I said there was one more way I could have attacked this. What if I had started by multiplying numerator and denominator by e to the x? Could I have started it that way? Now, why would I do that? Because then I'd get rid of all the e to the negative x terms and I'd have ones. And then I could have attacked the problem from that point of view. No matter what, we're going to get this as an answer. Okay, so that's this technique. Now there is one more type of problem that I want to illustrate today. I think it was just one more. And this one's going to take the longest.
Wait,
I
could you
have-
simplify the answer further?
No, that the final thing was the answer. Log of e to the x plus e to minus e to the negative x.
I couldn't, so you can't make it log of e to the x, then minus log of e to the
Oh,
negative x.
excellent question. Okay, let's do something here. Log a plus log b, log a minus log b, log a to the n. Are there manipulations for these three?
Yeah,
So we say the sum of the logs is the log of the product, the difference of the logs is the log of the quotient, log of something raised to a power is the power times the log. Those are absolute rules. So here's the question. Are there manipulations for these three statements that look very similar?
No, I don't think so.
No. And that's where, by the way, if people make errors in the logarithms, it's because they know this rule and they want to apply it to this. So that was the question just a moment ago. It's very easy to get those switched around. This cannot be manipulated. The log of a sum is just, yeah, there's nothing you can do with that. So in our situation where we had log of e plus e to the x plus e to the negative x, I can't go any further. The log of a sum is not anything. It's the sum of the logs that's the log of the product. So these three, if I have them, I'm done. That's it. Those would be my answers. But that's a very good question, because that is the one place, if people are going to get confused, that's where they get confused. So now the last topic we're going to look at, I affectionately refer to this as the evil trig. Okay, there is something that I would identify as evil trig, and this is not the trig you've done before. This is not any trig you've ever seen before. This is a form of substitution where I have something triggish and it is so out of control, but I can't answer the question any other way. Now, we know a tremendous amount of manipulation when it comes to trig functions. So I'm going to give you a simple example. If I had something of the form, I'll start with something easy, 1 plus the sine of x. And whether I want to graph this, whether I want to take the derivative of this, whether I want to take the antiderivative of this, I can manipulate this because I don't like that. In fact, in general, we do not like trig functions in the denominator of anything. They're harder to work with. So if this was the statement, this is, by the way, this is the first hour of my first Calc 1 lecture every semester. I do trig manipulation. One of the things I would probably start by doing is I would do this. Okay. Why?
Isn't it 1 plus cosecant?
Is it 1 plus cosecant? It's a little bit more than that. Okay, because I can't do anything yet. Remember, you can't break up the denominator. You can only break up the numerator. So you're wanting to break it up that way.
Yeah, that doesn't work.
No, a plus b over c is a over c plus b over c. A over b plus c is not a over b. Yeah, can't break it up that way. I can only break it up this way.
Oh yeah.
Yeah. And these are the kind of mistakes, if we make them, we can have flawless calculus, but we make an arithmetic mistake.
Now you can see why I went down so many rabbit holes with my quizzes.
By the way, lack of certainty of algebraic techniques is probably the #1 killer of any calculus student, because we understand the calculus, but navigating towards the end means I like the rabbit hole term, means I got to navigate through all the potholes of algebra that I'm not necessarily certain about. And that's why certainty is so critical. Now, my denominator is 1 minus sine squared. I'm showing you some simple manipulation because this will come in really handy today. Now that's 1 minus sine x over cos squared x. So can I manipulate this further? Yes. Now I'm going to pull them apart. So now I'll write it out. I have 1 over cos squared x. I have minus sine x over cos squared x. Can I manipulate this? Well, what's the reciprocal of the square of the cosine?
Secant squared.
I have 1 over cosine times sine over cosine. Oh my gosh. So this is equal to this. And if I asked you to integrate this, I'd be asking you to integrate this, but that would just be tangent minus secant, which is easy. Integrating this, impossible. There is no trick I could do on that one. So understanding basic trig manipulation, applying nothing more usually than just Pythagorean identities, maybe an occasional double angle or something. If I am aware of the things that are legal, I can do this. I love doing stuff like this. And I do this early on in Calc 1 to show people the things you might be able to do. Why did this work? Because that was a 1. So now what? Now we're dead in the water. None of the stuff I just did will matter because there's no Pythagorean identity I can do with the 2. In other words, I can only do certain things if I can apply Pythagorean identities in the way I did. If I put anything other than a 1 right there, I'm dead. There's no manipulation I could do to this from a trig standpoint. I can't let u be something. So evil trig is to address this problem. The problem that you cannot do the trig manipulation. We did problems a few days ago where we took trig integrals, we applied things to them, and you guys did a really good job of answering the questions. But that's because they were set up in such a way that I could apply Pythagorean identities. I've just created a situation where you can't. So none of that stuff will work anymore, yet I still need the answer to this question. So we're going to do a completely different set of substitutions, and I'm going to derive them from scratch, and then we'll do an example. I don't know who figured this out, but it was pretty genius, actually, to say the least. Make sure I have a problem written down somewhere. Oh, there it is. That one I'm going to do. All right. So what we're going to do is we're going to start with a substitution, and the substitution we're going to start with might seem a little odd at first, like why are we choosing this? And I'll walk you through it. We're going to start by saying, let u be the tangent of 1/2 x. Now, remember, we're starting with an integral like I just did, 1 over 2 plus sine x. So my trig functions are all functions of x. So right off the bat, I'm actually changing the argument. And the reason I'm doing this is think about the graph of the tangent function. There's some reason behind this. If I think about the graph of the tangent function, we know this is repeated forever and ever and ever. If this is x equals negative pi over 2, and this is x equals positive pi over 2, there are vertical asymptotes every pi forever. So the next one's at x equals 3 pi over 2, 5 pi over 2, and so on. But if I said this, oh, now the asymptotes are at negative pi and positive pi because of the over 2. So that means that this function is continuous, differentiable, defined for x between negative pi and pi. Now, why is that important? Because if I think of the unit circle, where's negative pi? That's right here. Where's pi? That's right here. Negative pi to pi would mean, that means this is continuous everywhere except right there, which is really powerful. I have no discontinuities. I have no weirdnesses. That's the formal mathematical term. There are no weirdnesses anywhere on the unit circle except right there. So this definition automatically gives me a really big interval to play with. I can pretty much use the whole unit circle. So I don't have any places where I have to worry about things being undefined or crazy stuff going on. Now, starting with that statement there, I want to derive the sine and the cosine. So what we're going to start by doing is using the fact that I know that, I'll write everything down so we remember. I know that the secant squared of theta is 1 plus the tan squared of theta. We know this, correct? Okay, so if I am using this as my angle, then that means I'm only considering the first and fourth quadrants for the original angles. Then the secant is strictly positive. So I can say this is true. Okay, so I can start with the statement like that, or I can go in reverse. So I'm going to start with this statement right here. Okay, this is a true statement. Therefore, the secant of 1/2 x is equal to okay. But if the tangent of 1/2 x is u, then that means that this is the square root of 1 plus u squared, based on this substitution. So right off the bat, we have the ability to state the cosine function. Therefore, the cosine, okay, of 1/2 x is this. Now, eventually, I want to be able to express sine, cosine, and tangent of x, not just of 1/2 x. But based on this simple algebraic statement, I know that statement is true. Okay. Now, what do I know the relationship between tangent?
Wait,
sine,
how do we know the cos and the secant have the same?
Oh, I'm sorry.
I was just about to ask.
Thank you. I saw that and I got excited. Yes, reciprocal. Thank you for catching that. That would have been really weird later. So I've got something for the cosine. Now, what's the relationship between sine, cosine, and tangent? You know that the tangent is the sine over the cosine. So in general, what's the sine theta? Wouldn't that be the cosine times tangent? Right? If tangent is sine over cosine, then sine is, do you agree with that? So therefore, what's the sine of 1/2 x? It would be this times this. So now I'm at u over 1 plus u squared. I just multiplied cosine times tangent. Okay, so with this substitution, that would mean that the cosine of 1/2 x and the sine of 1/2 x are these quantities. I'm not concerned about the cosecants and the cotangents. They're easy enough to get. Question? We're far from done. I'm just getting to this point because now I need the sine of x and the tangent of x and the cosine of x. I need to get those guys. So how do I get those? Well, that's where
Double angle.
double angle form. Exactly. Beautiful. Now, let's start with an easy one. What is the sine of 2 theta?
2 sine theta, cosine theta.
I'm sorry. Okay, so what if my theta is 1/2 x? Then doesn't that mean the sine of x is 2 times the sine of 1/2 x? Does everyone see what I just did there? Is this statement true? If that's true, is this true? Nicole?
Yeah. Yes.
Yep. So now we figured out a way to write sine x. We've got sine x. I'll put it right here. Because the idea with evil trig is I need sine, cosine, and tangent in terms of u. Starting with this, I got to get everything in terms of u. So this was the first one. So this will be 2 times this times this. Oh, but when I multiply those denominators together, 2 times the sine of 1/2 x times the cosine of 1/2 x will leave us with what? 2 times this will just be what? 2u over 1 plus u squared. Well, that wasn't so bad. Now, how do I get the cosine? Well, I'll just use one of the double angle formulas to get the cosine, but I want to use one that involves sine. I don't need this anymore. So I'll remind you of the trig. We know that the cosine of 2 theta is cos squared theta minus sine squared theta. We know this. So if I replace the cos squared with 1 minus sine squared, then this would become 1 minus 2 sine squared theta, correct? That's one of the versions of the double angle formula. Therefore, the cosine of x should be 1 minus 2 times the sine of a half x squared. Using the same reasoning, that angle is twice as big as that angle. So now I need to do 1 minus 2 times the square. I'm sorry, 1 minus 2 times the square of this. So let's write that out. So this would be 1 minus 2 times u over 1 plus u squared under the root squared. Well, one nice thing is I'm not going to have any square roots. So this will be 1 minus 2u squared on top, 1 plus u squared on bottom. So I'm going to replace 1 with 1 plus u squared over 1 plus u squared. So I have 1 plus u squared minus 2u squared. That'd be 1 minus u squared over 1 plus u squared. So now I can say that the cosine of x is 1 minus u squared over 1 plus u squared. And with that,
Professor,
yes.
could you go back the 1 plus u squared over 1 plus u squared minus 2u squared over 1 plus u squared? Where did you get the 1 plus u squared over 1 plus u squared?
That's
Oh,
one,
okay,
anything over
got it.
anything.
Got it. Okay.
Since
No, yeah, I
forgot
didn't
all
hear what
this
you
stuff.
said, and so I was just confused.
Yeah, no, it's all right.
Okay.
I need a common denominator, so I just rewrote that.
Sounds
This was easy, but I got 1 minus this, so I got to make it look like that. Now, so far, hopefully you notice this. My sine and my cosine are both rational functions. That is powerful. There's nothing triggish and there's no roots. Now, the easiest one of all now will be to state the tangent, because the tangent is just going to be the quotient of these two. Let me erase this. We're almost done. We only have 2 things left to do, and one of them is tangent. So the tan x is this over this, so the 1 plus u squareds will cancel, and I'll get 2u over 1 minus u squared. Okay, everybody see that one? So that's just beautiful. Okay, so I've got the tangent function, and lastly, now there's one more piece of the puzzle that I need, because when I do this type of substitution, I'm going to be changing everything. What about the relationship between du and dx? Okay, all my trig functions I'm going to be replacing with u-ish things, but that means I'm going to be replacing the dx with something du-ish. That's a word, sort of. Okay, so let's go back to the original definition. I don't need this one anymore. Go back to here. I need dx equals. So I got to get the x by itself. How do you undo a tangent? With an inverse tangent.
arctangent.
Inverse tan. Exactly. By the way, I'm glad you said that. Arctan and inverse tan are not the same. If somebody told you, they lied to you. Arctan has an infinite number of results. Inverse tan has 1. Inverse tan is called the principal arctan, but the term arctan does not imply a unique answer. This, by the way, if you didn't learn this, I get kind of mad that people stop teaching people this, and instructors get lazy. If I say the sine of pi over 6 equals a half, I think we all agree with that. If I said solve sine x equals a half, is the answer pi over 6?
Well, not only it's another. There's multiple possibilities.
In fact, it's pi over 6 plus 2k pi. It's
Yep.
5 pi over 6 plus 2k pi. Yikes. So if I say arc sine of 1/2, well, that's the answer. No, that's the infinite number of answers I just said. Arc sine of 1/2 is pi over 6 plus 2k pi, 5 pi over 6 plus 2k pi. Arc sine means every solution. It does not mean inverse. It has never meant inverse in the history of inverses. Now, there's a term that you'll learn in your upper level classes called principal. The principal arc sine, that means that the one that will satisfy, is called the inverse. That's why mathematicians never use the word arc. They use the word inverse because they don't want the ambiguity created. In pre-calculus, you guys did something called de Moivre's theorem. You may not remember it, but it was something like this. If I said, what is the square root of 9? You say it's 3. If I said, what are the square roots, plural, of 9? Now I want 3 and negative 3. I want the 2 numbers that when squared gives me 9. That's the correct answer. If I said, what is the 4th root of 1? You would say this is the number 1. If I said, what are the 4 4th roots of 1? It'd be 1, negative 1, I, and negative I, the imaginary number. Do you guys remember doing stuff like that? You go, oh my God, it was mind boggling. So if I say the square root of 9 is 3, technically it's the principal square root of 9 is 3. That's always implied that we mean the principal one. But it turns out the higher you go in mathematics, when you say square root, you actually are including both as possibilities, unless you're saying it in a form that it's a functional answer. I know that's mind-boggling, and it's like, it changes all the rules. I hate when people say, everything I've ever been told is a lie. That's not quite true. It's just the truth has been withheld. A significant percentage of the math you've learned will be complete. By the time you get to differential equations even, most of the math you've learned in your life will be completely rewritten. Almost all algebraic concepts you learned were not true. For example, you can't take the log of a negative number. Actually, you can. It's just complex. Yeah, you take logs of negatives just as often as you do positives. It's just, it's a complex number. But sine and cosine can only return values between 0 and 1, or excuse me, between -1 and 1, if I put real input. But if I'm allowed for complex input, sine, cosine return the entire number line, positive, real, and positive, or negative real numbers ever. Yeah, all the restrictions you've ever been told are not true. They're only true in certain situations. In other words, we're kind of sheltering you from the total truth. So anyway, I've never in my life used this, and I was lucky to never have a professor in my life to use this, because they explained it to me early on. You know, inverse. Don't create ambiguity. So that's what the inverse is in that case. So I want the inverse tan. So 1/2 x is the inverse tan of u. Therefore, x is 2 times the inverse tan of u. Oh, that makes it simple. I'll give you another example. There's no such thing as a derivative or an antiderivative formula involving an arc function, by the way. You can't differentiate an arc function because there's an infinite number of possibilities. You can't get an arc function as an antiderivative. So if you actually went to a website and it gave you, it'd be like getting an inverse cosine as an answer. You can't. It's actually not possible. It's like getting a log of a different base as an antiderivative. You actually can't. You can only get natural log. So I need the dx. So the last piece of my puzzle is right here. What does dx equal? Well, what's the derivative of inverse tan of u? Isn't it 1 over 1 plus u squared?
Yep.
Well, I got a 2 right there. So it'll be 2 over 1 plus u squared du. This is what makes Evil Trig evil, coming up with these. But once I have these, it actually makes impossible integrations doable. I don't want to say simple, doable. We'll do an example of one. So the way it starts is if I recognize I have an evil trig. How do I know? Because none of the techniques I know and have ever learned are going to apply to that problem. I look and going, you know, I don't know how to do that. Let me try the evil trig. So I start with this statement here. I make these substitutions and I create a rational function that I guarantee you can integrate using things like partial fractions decomposition and such. No more substitutions are necessary. Now, at the end of the problem, we have a small problem at the end. At the very end of the problem, when I do all of my stuff and I substitute back for the u's, I'm going to get tan of a half x in my answer. But my original question only had x as the argument. So I'd really like to know, how do you get from tan of a half x back to something involving x? Well, there's actually a very simple trig identity. Okay, and the simple trig identity, so I wrote it down, the one I want you to use, it's in every calc book. There's a simple trig identity where it says the tangent of the tangent of a half x, okay, let me make sure I write in the right order. The tangent of a half x is 1 minus the cosine of x over the sine of x. This is an identity. Now I can manipulate that all day. Why would I do that? Let's just break it up. 1 over sine x minus cos x over sine x. And you get your 2 favorite trig functions, don't you?
Cosecant minus cotangent.
If u equals this, then technically it's this, but these are not useful because I needed the halves to do everything. At the end of the problem, when my final answer involves, you know, tangent of a half x, I can just simply replace it with this. I'm going to show you. The textbooks never do. But here's the problem about trying to, if I have an answer where all my arguments are a half x in the answer, but they were all x in the question, if I want to check it through differentiation, it won't work. I can't take the derivatives of the functions of 1/2 x and expect to get back my original integrand that was involved with x. So that's one of the reasons for doing this at the end of the problem. But if you
Professor-
don't, it's actually not life and death either. Yes.
When we get a problem with Evil Trig, can we use the equations that we just came up with, or do we
That's
have
what you're
to-
going to use. Yeah, absolutely, that's what you're going to use. You're going to use the ones you just came up with.
So what we came up with was just like a proof, so we don't have to like let u equals tangent of half x and go through the process in each problem, right?
Do you have to re-derive them? No. No, that's, so I'm
On
going to
an
walk you
exam,
through
I mean.
how it looks and how it works. Okay, do you see
Okay.
this problem here? My coefficients are just all wrong. If my coefficients were the same, then I could factor it out and it would be a simple case of conjugating like we did before. If these were both 3s or both 2s, this is actually a fairly simple problem. But because they're different, there is no trig identity I can perform. Well, what about multiplying by the conjugate? All I've got is a more complicated expression now because I can't use any trig identities because I need 1 plus trig function or 1 minus trig function to make that work. So this is a candidate for evil trig because you have no techniques to address this. There's no u sub that will work like the usual. I can't make the denominator u, I have no chain rule factor. I can't make the denominator, the cosine, I don't have a sine. This is an evil trig because really the coefficients let me down. So the question is, how do I address the problem? I don't want to re-derive these. No, I just derive these. These are now facts. This is law. You don't ever have to re-derive this. You don't have to re-derive how to do an integration by parts again. You now have that. That is a tool. So we will. The only thing I need
Thank
to
God.
start by saying, let u equal this. I need to start like that because that's the impetus for now using this. Because of this statement here, all of this would be a result of this. Does everybody understand? We started with this, we derived all of this. All of this is a consequence of that statement. So I really have to start with that statement. I don't have to do anything else. Now it's just plug and chug. If that is true, then this is true. And you get to use this. Like Yaman was asking, you do not re-derive this. If you want to for fun, go ahead, but don't do it on an exam. It takes too long. So what am I going to do? I'm going to rewrite this using this. Okay, so what have I got? I have 3 plus 2 times 1 minus u squared over 1 plus u squared. On top, I have 1 over, but now my dx would be 2 over 1 plus u squared, and I'm all integrating with respect to u. If I walked away right now, of course, I don't have an answer, but this is a rational function. After I'm done simplifying, that will simply be a quotient of polynomials. And absolutely guaranteed, you can always integrate a quotient of polynomials. There is no exemption. When I say you can, doesn't mean it's easy. You can. That's what partial fractions decomposition taught us. Oh, because I can always factor, I can do that kind of stuff. So off to the side, we can clean this up off to the side. So on the denominator, the easiest way to attack this, don't put these over a common denominator. No, just distribute this. So I would have 3 times 1 plus u squared plus 2 times 1 minus u squared, and then these guys would cancel. Do you agree? So this times this plus this times this. And that would be 3 plus 3u squared plus 2 minus 2u squared, or 5 plus u squared. So right now, here's what I got. I have a 2 on the top. I have a 5 plus u squared on the bottom. Oh my goosh. This with this, replacing this, I get this. And that's easy. Can you give me the antiderivative as the next thing? Yes, there's no work to perform. Now, I have a 5. What should you be seeing?
I had 5 squared.
Right, I did, but not 5 squared.
I said rad.
Oh, I'm sorry. I've never heard a human being say rad as root. that you got from somewhere, obviously. Yeah. Okay, so Why would I want to do that? Because this is the form of what? What is the form of this antiderivative?
A squared plus X
So
Tangent.
what function? I'm sorry, what function is it going to be?
the tangent. Wait, if you is that
You're half right. Tangent's in the answer.
it's a tangent X? Do you make A equals?
Is it tangent, folks?
Oh, inverse tangent. you mean.
Inverse tan. There we go. I said
Okay, okay.
tangent.
I was thinking of trig substitution.
No, we're there.
Okay.
Okay, so let me write it out. Okay, do we agree that it's going to be inverse tan of 1/√5 times u? This shows up on the outside. I had a 2. So far, so good? Stare at that for a moment. Are you happy with that? Is that okay so far, everyone?
I want to say yes, but your tone tells me no.
No. We overcomplicate things. He said this is the form of an inverse tan. There's no substitution. It's a squared plus u squared. Boom. Just making sure that the √5 goes in the right place. Now we're completely done with the calculus. Now we substitute back. And what substitution do we perform? Right there. This, by the way, this is why it's so critical you start by saying let u equal this, because my final answer is going to have a u in it. Oh, I need to know what to substitute back. So
Wait, inverse tan, and if there's a tangent inside, do they cancel out?
Yes.
not exactly. Not
Isn't
exactly.
it just on a specific range?
Well, 10 trig function of the inverse trig function I can always undo. But inverse trig function of the trig function, I can't necessarily. If they're the same ones, I might, but the problem is I have coefficients. The coefficients kind of mess it up, unfortunately. If I said inverse trig function of thing, then it will be thing. The problem is I got this.
Well, what do we do now then?
You just leave it in that form. So my answer is going to
Oh,
be
all right.
inverse tan of 1/√5 times what? Times this. Everything I said is true and correct, but remember what I said about my it is an awful looking answer, but this is pretty common. I have inverse tangent of stuff involving tangent, but not of x. I have tangent of a half x. And I showed you a way of getting around that. This is perfectly correct answer. Right? This is what every calculus book's going to give you. Problem is, this is not a very useful answer because I changed my argument. How do I get it to be a function of x? Well, that was the little cosecant cotangent thing we just did. So all I'm going to do is I'm going to change this. Cosecant x minus cotan x. There. That's it. That's how you get it back to a function of x. Now, even if I could manipulate tan of the inverse tan, the coefficient in front can't be pulled out. So there, I can't do any kind of manipulation here. If I could, I would. Now remember, the rule of thumb on simplification is you take any simplification if it's obvious. If you're not sure, better to leave it alone rather than risk saying something that's not true. So probably the best answer I can give to this question is this one, because it's back to a function of x. I really don't want to check this one, but if I were to take the derivative of this, an hour later after simplifying, I should get this back again at some point. Now, again, I call it the evil trig because it only applies in certain situations and it required this substitution. But the beautiful part about this is I took something I cannot answer, I made it into a rational function. Okay, that's really what it comes down to. And a lot of it is recognition. So let's go back to, again, stuff we know. You have an integral, you see trig functions. You already know if you can do it or not. If you saw something like, I don't know, 1 minus the sine of x over the, I don't know, let's just say over the secant of x dx. Is this evil trig or is this just simple manipulation, rewrite it kind of problem? What do you think?
Simple manipulation, because now you can split them apart.
I can split them apart, or I can say, let me multiply top and bottom by cosine. And if I do that, oh my gosh, I can integrate that, I can integrate that. Life is good. I love this problem. This one makes me happy because of the form. If I had written it as secant x over 1 minus sine x, I cannot pull it apart, but we did that trick earlier. I could conjugate the denominator, eventually get it to be cos squared, then I pull it apart. So again, simple trig manipulation. How do I totally mess this up now? Put a coefficient in front of either term. Now there is nothing I could do.
And is that the only form of evil trig when there's like weird coefficients?
Yeah, it's not the only form, but when you see coefficients that are not ones or can't make ones, the original problem, and I want you guys to understand how subtle the difference is. The problem that I asked you,
3 plus 2.
what if this had been the problem?
So yeah, you can factor it out.
You would do this, I would hope. Then you'd multiply top and bottom by 1 minus cos over 1 minus cos. You'd simplify it. Now it's a really, really simple integral. It's the form. Because these numbers were the same, I could do this, and now I have my 1. It was because those numbers were different. All right, so I have this problem. Okay, I have this problem. Evil trig. Evil trig alert. I just threw another function in there. There's nothing clever I can do. You recognize evil trig because you look at it and go, I don't know any other way of doing it. It's probably evil trig. This is a minor technique. It is not a major technique. Partial fractions decomposition, trig substitution, integration by parts. Those are the big three. We've looked at several different types of problems today that are very, very specific. I would like people to be able to do an evil trig problem. I will ask you one evil trig problem on the exam. I mean, you have the option technically of skipping it. Okay, I think I've asked you one on the next quiz, and I think I even made it a bonus problem. But it's a technique that when it comes up, you want to have a way of answering the question. Does it come up a lot in math? No. No, not in math.
This is also one of those things where we can put those sine of x, cosine of x, and tangent of x equations on.
Oh yeah,
that.
yeah. I would hope you do. No, you don't see a lot of evil trig in math. You know where you see a lot of evil trig?
In physics.
In physics. Oh yeah.
My favorite subject.
The worst trig you ever see, you will see in physics. And then you'll get to the place you're going, I don't know what to do with this. It's not that you have to know everything, but you have to know there is an out more than likely for everything. And I say the next thing in all seriousness, because the majority of the students I work with, unfortunately, are not going to be math majors. I mean, I try my hardest to convert you all to the dark side, but I'm not very successful. I know I'm teaching mostly engineers. When you're an engineer, you know what you know, and you know where to find the things you don't know off the top of your head. You have to know certain things. You have to be able to problem solve. You have to be able to think on your feet, but nobody knows everything. You know the common stuff, you know the stuff you work with, but the obscure stuff is a little trickier. But if you know there is an answer and where to find the answer when you don't know it off the top of your head, then for all practical purposes, you might as well know it because you know exactly where to find it. People say, well, I'll just go on the internet. I'll tell you right now, if you type in a question on the internet, more than 90% of all websites dealing with math will give you an absolutely incorrect answer. The one I trust the most, Wolfram, 1/3 of the time, either gives me a completely wrong answer or says it can't answer the question that I've already answered by hand. There's no such thing as a flawless website. Some of them are really, really terrible. And I can always tell when people went to one of those terrible websites because they give me an answer that only the internet could produce. And it's wrong, by the way, because it's a programmer who programmed it. The computer's not thinking it. Somebody programmed in the answer and they didn't know how to do the calculus. No, but it's nice when you know how to do things or how to find things. Okay. My closest friend in grad school was a chemist, went to UCSD, and he worked in a lab 24 hours a day, and he did certain kinds of experiments and he did research. And I said, wow, do you know everything about chemistry? And he would laugh. He goes, I don't know 1% of chemistry. He says, I know the stuff I work with, but there's so much more. But he says, I know how to find the answer to every question. I know how to find the answer to the stuff that I don't do in case I need it for later on. And that's really important, okay? So anyway, we'll go ahead and stop here.